it was important. So, good afternoon once again. I'm Geeta Yadav. I'll be speaking on building a semantic knowledge wiki base for synthetic phytochemistry. I work jointly in India and in the UK at the University of Cambridge. I'm the co founder of semanticClimate.org. It's a citizen science movement, and we are very interested in developing AI over NLP to make different kinds of data sets accessible. It was a pleasure listening to the two speakers before me. And my takeaway from both of these talks was that we all do need wiki affiliate collaborations to truly overcome our regional or region specific issues that we have in our research, and particularly for addressing global challenges. So, we have been part of the Earth Metabolome Initiative, a global effort to provide, to profile the metabolic content of all currently known species on the planet. And our goal, I'm a very, very small part of this mega international initiative, and my particular role in this is to bring phytochemistry or the landscape data to become available publicly to as many people as we can in this among the citizens. It's part of a national mission in my country, India, the biodiversity mission, and our focus particularly is on climate security. We are trying to unpack plant chemical arsenals using open science strategies, which is what I will talk about today. We've been trying to create the first and the largest machine processable climate to species data repository, and that is what I'm hoping to get help from our listeners today, or inputs or comments about. This repository, we have already are creating it, and we intend for it to be accessible and embedded in Wiki, the global knowledge graph. And we intend to, in the long run, train it to detect as well as predict climate change with minimal human intervention. Having said phytochemistry, I am a plant biologist. My interest is in plant communication, and plants are perpetually always communicating with each other through tiny, visible, invisible chemicals called phytochemicals and volatile organic compounds. Our work is to analyze, detect these emissions, and then analyze them. And in general, how would you know, what chemical is being emitted? Plants are constantly altering their emissions based on the species, the stage, the location of that species, many tissues, other conditions, and a large number of variables are there. Most of this data is published in papers, so we require published papers to extract this data from. And this is just a simple example of one pepper species from Brazil, where all of these different chemicals are being emitted in the oil of the pepper species. You can see pinene, saponine, and you can also see to what extent these are being emitted at. Similarly, this is another paper presenting the same kind of information. The table, you will notice, is very similar. It's got rows with the names of the chemicals. So the chemistry is in the rows, but the columns would have very different kind of information depending upon, is it species, is it the part of the plant, is it the root or the leaf or the flower, or is it 4 different varieties, or is it 3 or 4 different locations? And it's very difficult for a human being, or for a machine therefore, to detect what the column information is about, even though the chemistry can be understood from the name of the rows themselves. So therefore, the problem or the challenge we are facing is that all of these different papers with all of the different information have to be put into this repository that we've been creating. And how do we make sense of, how do we automate this without manual intervention? Because there might be hundreds and thousands and, more papers there. First problem is we don't have access to all the papers, research papers. So we have an access issue. And so improving access is one part of the work that we do. And of course, a lot of people wonder about access and whether availability is the same as accessibility. And we say that we've been talking accessibility all this while, but we've been doing availability of the data. Our aim is to make every piece of information, just as Wikimedians do, to make it machine exportable, machine processable, exportable, comprehensible, and actionable. And for that, we don't like PDF. So we want to be able to free ourselves from the tabular data sets that I showed you just now in different papers that we get these tables. It's nearly impossible to extract these tabular data sets or the knowledge from these PDFs. And so therefore, most of the time, access to the information that's already published is denied to us. It's the same way with the IPCC sixth assessment report, where we established our tools first. That much of the world's information, the most important knowledge in the world, is always locked in PDFs. And so, therefore, coming back to our chemistry, phytochemistry work, we got help from Carl Malamud, publicresource.org in America, who provided us the metadata of 107 million articles. Now, with 107 million articles having 9,000 plants and information on almost 2,000 different chemicals, I'm in no position to manually extract these tables. And so, therefore, we are trying to do it automatically, and that is where we need help. So, we've found that there are more than 39 million combined instances of chemicals and plants. And we want to put that into the database that we are creating in Wiki. And the solution that we found is to build a Wikibase RDF data model using where has it gone? Hello, the triplets. We are working on the triplets with. So this is our network of people. There's Peter Murray Rust at the University of Cambridge. There's Simon Worthington, who is at Berlin. Axel is also in Berlin. We have a huge number of intern students in India, both from rural and urban India, who have been building the student authored toolkits for extracting knowledge from PDFs and embedding it into Wiki. And we do all of this by learning. This is our knowledge extraction using AI protocol. Once we've got the final AI over NLP outcomes from the PDFs, which we convert to HTML, and then get the knowledge phrases out, we build a semantic workflow. And while creating the Wikibase triple from that workflow, we search for plants, of course, chemistry, of course, and the relationship. Does a certain plant produce a certain chemical? And the kind of triplets, therefore, that we have are plant with a relation and chemical. Pine, for example, makes pinene. Lantana lacks xanthine, and so on. The benefits in this is, of course, as the previous speaker already mentioned, and I think it's wonderful that all of us agree jointly that accessibility and barrier to entry to creating Wikibase instances has really been simple for us. The ease of use for interns who have absolute zero barrier to zero background knowledge has also been wonderful. They've been able to do great work with us and expand on the resource creation. But the challenges are things more biological. Challenges are like how to normalize all of this data that we get from different kinds of tables with completely varying names of columns there. And we all constantly find new terms, new variables that come in to modify a plant's emission. Also, synonyms. Sometimes a certain chemical may be called something else, and a certain plant may be called something else in a different country. So we are trying to now build in Wiki's multilinguality to overcome our issues with certain kinds of synonyms. And we've also had major issues with phrases or new terms, sometimes, which are not there in Wiki already. And we are trying to bring those in by embed them using the Wikibase instance. There are other kinds of triplets we may also have, as I said, for each variable that the plant emits, not just whether a plant emits a certain chemical or not. There could be issues that it emits that chemical only in that location. So then our triplets change and become plant location chemical. For instance, the pine releases pinene, but only in the Himalayas. The rhododendron makes the granotoxin, but only in certain regions, such as Europe mostly. In India, it does not make the granotoxins, and so on. All of this information, as I said earlier, has the 39 million combined instances that we've been developing have led to issues with visualizing data. And that is also where we've been greatly assisted and supported by the Wiki model, where we perform automatic indexing using dictionaries that we create out of these words that we have found on the Wiki in our documents, the plant names, the chemical names, and then we try to build an obsidian network out of these to make the text semantic. And as you can see, these networks are interactive. We can test different areas of the written document. We could extract information. We've been able to do it at single document level. We've not been able to do it at large document level, but for now, we've opened access in these multiple ways. And we have been able to, at a smaller scale, make our data available, machine readable, exportable, comprehensible, and actionable. But I would like to end my slides by saying that it's not that easy, and we would love to hear more about, how to make our triplets, how to generate automatically all our triplets using the kind of information complexity that is there in the data, in the papers themselves. You're more welcome to see what we are doing and join us. We are a citizen science movement. You can find us at semanticclimate.org. We are all of our work is on GitHub, and I take this opportunity to thank my colleagues Peter, our intern Shweta, program manager Renu, and all of our partners, Simon, Axel, and others, for helping me put this together today. I hope I'm in time. I was told there's a very limited time to talk about our work. I hope this made sense. Thank you very much.